Respiratory diseases are among the leading causes of morbidity worldwide, and early, accurate assessment remains a major clinical challenge. A key element in this evaluation is the analysis of adventitious respiratory sounds, such as wheezes and crackles, which are abnormal respiratory sounds typically present in cases of respiratory diseases, making them extremely important clinical biomarkers. These sounds provide critical information for the diagnosis and monitoring of conditions like asthma, COPD, or interstitial lung disease. However, their interpretation is often subjective and highly dependent on the clinician's experience, which can lead to variability and missed insights. At the same time, understanding the respiratory airflow is essential. By estimating airflow directly from sound, we can determine where each adventitious sound occurs within the respiratory cycle, whether during inspiration or expiration, adding important physiological context to the analysis. To address this, we developed an AI-based application with a simple workflow. First, respiratory sounds are recorded using an electronic stethoscope, a microphone, or even a smartphone. Then, the recording is uploaded to the platform. Our AI models automatically detect continuous and discontinuous adventitious sounds and estimate the respiratory airflow. Finally, a structured report is generated for clinical interpretation. These acoustic biomarkers can help clinicians diagnose their patients, provide better management by adjusting medication, for instance, and monitoring their evolution over time. This approach provides an objective, scalable, and clinically meaningful tool supporting healthcare professionals in improving diagnosis, monitoring, and ultimately, patient care. In this clip, we see a demo of the application in which 2 respiratory sound recordings have been uploaded. The application interface is divided into 3 major sections. After the user uploads a respiratory sound recording, the first section will plot the raw audio waveform. On the second section, a time-frequency representation of the audio will be presented. Then, after the user runs the inference models, the 2 bottom sections will be updated. In the second, the identified events corresponding to adventitious sounds will be presented, whereas the third section will display the respiratory airflow, allowing to discriminate the breathing patterns of the subject being recorded. The user can load multiple recordings, and the results of all inferences will be stored for subsequent analysis.